Okay, so today first hour I'll solve some problems on multiple integrals. Next hour we'll start the new chapter. So first let me go over the proof of this problem which I wrote last time. The plane x over a plus y over b plus z over c equals 1, where a, b, c are positive. Cuts off cuts the ellipsoid x squared over a plus y squared over b squared plus z squared over c squared less than or equal to 1 into two pieces. Find the volume of the smaller piece. Okay, so if we want to draw the picture of this, you see these A, B, C's will cause a little bit of confusion. So the best way to attack such a problem is to change coordinates. Okay. Okay, so we first consider a change of variables. Okay, so the change of variables, remember, it's something like this. So this is the, let me extend this a little bit more. Okay, so U, V, W, we have a map T. I'll write the map here. And here we have X, Y, Z. Okay, so the map is X is equal to AU, Y is equal to B, V, Z is equal to C, W. So what happens here is that an ellipsoid here, so we have an ellipsoid like this. Okay, so this is what we see in the first part. So it goes like this into the other parts. An ellipsoid here. Okay, so this one, it becomes a sphere here. Okay, so it becomes it becomes a sphere. Okay, so okay, so the Jacobian of the transformation so that we denote like this. Okay, so we write it in this way to remind us whose derivative is taken with respect to who. Okay, so this is a determinant. So you see, so you take the derivative of this with respect to u, v, and w. The others are 0. So here you have a, 0, 0. Now for y you have 0, b, 0, 0, 0, c. Okay, so this is a, b, c. It's already positive, so you don't need to change sign. Okay. So note that, let me also mention this, note that the ellipsoid is now the image of u squared plus v squared plus w squared less than or equal to 1. Okay, so instead of x, you put au, so a squares cancel, you have u squared, so you get this thing. And similarly, the plane that cuts the ellipsoid becomes U plus V plus W equals 1. Okay. Tamam. Bir şey mi gördün? Yok mu? Peki. Okay. Okay, so the plane here, okay, so it cuts something like this here. Okay, so we have a plane here. It cuts something on this side. Instead of trying to visualize what happens there, here we come to a very simple description. We have a sphere and we have a very nice, easily described plane which cuts the sphere into two parts. Okay, so the smaller part is what we call the cap. So we want to calculate the volume of the cap. Okay, and then the Jacobian being fixed means that whichever volume you calculate here, when you transfer it to this side, it is multiplied by A, B, C. Normally, this expansion is pointwise. Okay, so normally the Jacobian depends on U, V, W. For example, in the polar coordinates, for example, as you move away from the origin, the expansion increases. So R shows up in the Jacobian. But here it says, with this nice change of coordinates, the expansion is constant. So we just calculate the volume of a cap here, and then multiply it by ABC, we obtain the volume cut here. Okay? So the volume that we want in UVW space is the volume of a spherical cap. Okay, so if you want to draw a picture, okay, so actually the picture is like this. Here is the sphere. This is how it cuts it, but let's turn it around and see, first of all, what we want to calculate. So here is the sphere, okay? And suppose this is R, okay? And here is a cap like this. So we look at this height. Okay, so we want to calculate the volume of this cap given radius and height. Height is measured in this way. Okay, so you can also consider this as height, but the formula doesn't look any better. We generally try to choose a parameter so that the formula will look better. But in this case, whether you choose this part or this part as your parameter, the formula looks similar. Okay, so so you want to find, so you want to calculate the volume of cap of height h in a sphere of radius r. Okay, so we have formulas for this, but let me remind you how we derive those formulas, because, okay, so this is an exercise. Okay, so one way of calculating this volume is the following. Okay, so we consider revolution. Okay, so we have here, let me see which one I'm using. Okay, so this is our, okay, let's say which here I use z coordinate. This is our z coordinate. This is h. Okay, so this part, so starting from here, this length is, this point is r minus h. This part is h. So I take an arbitrary point here whose height is z. Okay, and here this radius is r. Okay, so you see I want to revolve this. So I find the area of this multiplied by dz. Okay, that gives me an incremental volume. Then I add it from r minus h to r. So this point is r. This point is r minus h. Okay. So this, in our case, okay, so we can do it this way. So this height, if this part is Z, if this part is R, okay, so I know what this part is. So this is what? R square minus R minus H square, okay? So if I do this, this is Z square, so sorry. Okay, so this height, I'm talking about this height, not this height. This is the limit of, this is the range that Z changes. So this is R square minus Z square. Okay, so area, so let me do it again here. So I have this, I turn it around Z axis. So the area here, area is pi R square minus Z square. Okay, so it has a thickness is dz. That's how we interpret that. Okay, so don't tell this to anybody, but that's how it works. Okay, so we have a small volume. Okay, so total volume of this disk is pi R square minus Z square dz. Okay, we add all these volumes from Z equals R minus H to Z equals R. Okay, so that is we integrate. So this now here integrate. Okay, so the volume, let me check if I gave it a name. Okay, so volume HR is equal to integral from R minus H to R. Volume is pi R square minus Z square dz. Okay, so that's how you find the volume. Now, this is a simple polynomial. You evaluate that, simplify it, and you get pi H square R minus 1 over 3H. Okay. Now, check that it makes sense. For example, when H equals R, so we are calculating the volume of the hemisphere. Okay, so you see that it will be 2 pi R cubed over 3, which is half the volume of the sphere. And when H is equal to 0, you have H here, we won't have any volume. Okay, so the formula makes sense. Okay, so this is the volume formula for the cap. In our problem, now we have to find R and H. R is clear. Okay, so here R is 1. Okay, so let me go over here. So for our problem, we must find R and H. Okay, R is easy. So our sphere is U square plus V square plus W square equals 1. So R is equal to 1. Okay. So now we need to find H. Okay. So to find H, we draw a picture. Okay, so in the first octant, U, V, W. Okay, so this is our sphere. Okay, so let's make it look like a sphere. Parmağım kanser olacak bunlardan ya. Okay. So these points are 1, 1, and 1. So our plane, okay, so our plane is U plus V plus W equals 1. So when For example, V and W is 0, U is 1, so the plane passes from here, it passes from here and here. So let's draw it with the blue. So this is, in the first lockdown, this is what we see. This is the plane. Okay, so this corresponds, this part now corresponds to this part. Okay, so we have to find the distance between this plane and the sphere. That's the height. So we draw. Okay, so we draw an arrow here. It passes here. It comes and cuts the sphere here. Okay, so consider this one, this arrow. Okay, so let me draw all of it like this. Bu da pek ikna edici olmadı ya. Biraz yalan. Yalanın da bir usturubu olması lazım. Okay, so it should come this way, right? So it should go maybe like this. So when it intersects the plane, it is perpendicular here, okay? So this is a line through the origin. In the direction of the normal of the plane. Okay, so what we have is this. This is our sphere, and this is our plane in the picture, and this red stuff is this thing. Okay, so you want to find this distance. Okay. Normal of the plane, we can read it immediately from here. Normal of the plane is 1, 1, 1. So a parametric equation for this line, a parametric, let's say, expression for this line is phi of t, 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 right? When t is equal to 0, we are at the origin. So when does this line intersect the sphere? I have to find this point and this point. Okay. So when does this? So let me remind you that this is. Well, this is not. Well, I mixed two notations. Phi of t. Phi of t is t, t, t. Okay, so this is the line. So when does this line intersect the plane? U plus V plus W equals 1. Well, when you add these three, it must be 1. So the answer is when t is equal 1 over 3. Okay, so phi 1 over 3 is on the plane. So what is this length? Okay, so we find this length now. So here, phi 1 over 3 is here, and here is of course phi of 0. So the length of phi 1 over 3 is what? What is the length of this? We have a vector. Okay, so the length of this is 1 over 3, 1 over 3, 1 over 3. I want the length of this. So this is square root 1 over 9 plus 1 over 9 plus 1 over 9. What is it? Square root 1 over square root 3, right? Okay, now actually I need this distance. Okay, for this, this is now easy because this whole thing is 1, radius is 1. Is 1. So h is equal to 1 minus 1 over square root 3. Okay, so now we can put this into our formula. Hence, so VHR, so V 1 minus 1 over square root 3, R is 1, is equal to, okay, now the next is just a calculation. Okay, so I will do this calculation at the end. So hence, this is the volume of the cap in UVW plane space. Okay? So I'll do the calculation at the very end in the UVW space. Okay? The transformation T multiplies each volume by ABC, which is J. Okay, so the required volume in X, Y, Z space. Okay, so the volume of the small part of the ellipsoid cut off by our plane is, okay, so this is equal to ABC times V1 minus 1 over 3, 1. Okay, and this is equal to, after simplification, so I'll just write the result, ABC pi 2 over 3 minus 8 over 27 square root 3. Okay, so so this part is just, you put these things in, and then you simplify it until you are satisfied. You can also leave it like that. Okay? So this is approximately, if you calculate this part, you see this is a number times ABC, so this is 0.153 ABC. Okay? Well, this is a very typical example that change of variables makes life easier, but of course it depends on the problem. Sometimes in this problem, which change of variables will be suitable was obvious, but sometimes it's not very obvious. We'll probably solve some more problems. Okay, so any questions on this? Okay, so here the nice thing was that this Jacobian was constant, so we didn't do an integral here. If if this was a function depending on UVW, then we would try to look at the integral, and then you see just in spherical coordinates, for example, you have rho square sine phi. That is the Jacobian, so you cannot take it out. You have to integrate it. Okay, so that's one thing. So talking about spherical coordinates, here I have an example where we don't do any change of variables, but it's a nice problem. It ties it back to what we learned in high school also, bounded by the spherical coordinate surface rho equals 2 sine phi. Okay, so the problem says that life is taking place in spherical coordinates. Given one equation gives you a surface. Okay, so the problem suggests that this surface is a closed and bounded region, so it has a finite volume. Calculate the volume. Okay, so rho equals 2 sine phi is somehow a circle. Okay, so it looks like in polar coordinates, radius depending on the angle by sine or cosine is a circle that passes through the origin. In spherical coordinates, we have theta. So here theta is free. It means that you consider this circle in one plane, and then it turns around the origin in the z plane. Remember, even though we are doing these things in the spherical world, actually what we mean is everything is taking place in the XYZ space, but we express the situation in terms of coordinates, in terms of spherical coordinates. Okay? So there has to be a correction factor. Otherwise, if you just do this in the Cartesian space of rho, phi, theta, you have a different volume there. Okay? So with the understanding of that, our picture is like this. Okay, so let us do that here. This is Z, Y, X. Okay, so everything is taking place in the XYZ space. Now phi is this angle. Okay, and rho is, when phi is 0, rho is 0. When phi is pi over 2, rho is 2. So it's a circle like this. Okay, so consider it this. In the YZ plane, we are talking about this. This is 2. So this guy is rho equals 2 sine phi in the YZ plane. Okay, so now this is the region. Theta is free, so this thing is rotated around Z axis. So you obtain a symmetry without a hole in it. And we have to find the volume of this. Okay? Rotate this region around Z axis and find the volume. Okay, so that is how the problem now translates. Okay, so the volume is equal to, well, as usual, we'll take the integral. The correction factor, Jacobian, is rho square sine phi, d rho, d phi, d theta. Theta changes from 0 to 2 pi because I'm rotating this. And phi changes from 0 to pi, right? Because if you go once more, well, that's the limit of phi, then you just get this. And rho changes from 0 to this equation. Okay, so because if this is rho, it starts from 0 and it leaves the region when rho is 2 sine phi. Okay, so you see that this is now easy because this is just integral 0 to 2 pi d theta. So that guy is 0. Okay, so here, let's just write it. So this part is constant for theta, so we just calculate this, 2 pi. Now the other one is from 0 to pi. When I when I integrate this, I get 1 over 3. So I'll get 3 here. I'll get rho cube. Rho cube will be evaluated here. So that will be sine cube. I have another sine, so I have sine to the power 4 d phi. And I have here 2 cube, which is 8. So I put 8 also here. Okay, so this is what? 16 pi over 3 integral 0 to pi sine 4 phi d phi. Okay, so let's see if I get the same thing here. Okay, so at this point you have two options. Either you look it up in a table, because these things are standard, or just to flex your muscles, you can integrate this yourself. So I'll do both of them, but first I'll just evaluate this because this is known. I think it gives you 3 pi, so 16 pi over 3, and this thing gives you 3 pi over 8. And the answer is 2 pi square. 2 pi square. Okay, so for sine phi, we have the following thing. Okay, so let me do this over here. Integrate sine 4 phi using double angle formula twice. There are also, you see, you can, this is one way. You can look it up in a table and immediately find the antiderivative, or you can just give it to some software and you obtain 3 pi over 8. But just to see how things tie together, so you see that sine to the 4 phi is equal to sine square phi square, and sine square is what? 1 minus cosine 2 phi over 2 square. So this is 1 over 4 1 minus 2 cosine 2 phi plus cosine square 2 phi. Okay, but here again half angle formula, again use, so this is 1 plus cosine 4 phi over 2. Okay, so now everything is linear, you can integrate this. Okay, so this is also note that in this problem we can use Pappus theorem. Okay, so which was probably discovered 2,500 years ago. So did you hear about this Pappus theorem? No? Okay, Pappus theorem says that if you revolve, so this is the theorem, if you revolve a region D, say in XY plane, around y-axis, the volume obtained is equal to area of D times the distance traveled by the center of mass centroid. What is the name for this? I think it's called centroid. Centroid of D. Okay. So in our problem, D is a circle of area of radius 1. Okay. So this is our circle. So this area here is pi. Its center is, centroid is center at, in our case, 0, 1, travels 2 pi. Okay, because you see, this is the center of the circle. So this is 1 now. It turns around the origin and gives you a circle of radius 1. So its circumference is 2 pi. Okay, so this is 2 pi. Okay, so you multiply this and you obtain 2 pi squared. No integration. Okay, but of course this things is easier when you can recognize this part, the center of the region. If it's a bit more complicated, then there are again some integrals to find the centroid. But if you are going to take integrals, then you can do this. Okay, so we have to know several methods to attack a problem, because there is no one single method which solves all problems. Depending on the problem, you should be able to shift from one method to the other. Okay, so this is how Pappus used to solve it. Nice formula, nice problem which we can solve again in 2 different ways. I'll do it with spherical coordinates, and then I'll do it using this washer method which we learned last semester. So you see that our aim is to correctly set up the integral. So it doesn't matter in which coordinate system you do this, now that we have software available in real life. Okay, so in the exams it doesn't matter, because in the exam you'll be given a problem which you can actually solve by hand in 15-20 minutes. Okay, so that's not real life. In real life, whatever the problem is, if you set up the integral correctly, then most of your job is done. Then you give it to a software. If the software solves it, it's done. If not, then you change you try to find out why the software failed. Okay, and then you change coordinates and give it again. So one way or the other will work. So in this problem, so find the volume obtained by revolving the following, the shaded region. I'll draw it now, around, in this case, z-axis, I guess, region around z-axis. Okay, so here I have this. This is Z. So this part, of course, it doesn't matter which one is, but let's call this is Y. And here we have, first of all, we have a sphere. So this is x squared plus y squared plus z squared is equal to r. So we have, if you see, first we have a sphere here. In this sphere, we cut the sphere by two rays like this. Now, if you revolve this around z-axis, you obtain a volume. It's immediate to find the volume of this in spherical coordinates because you find the volume of one cone, subtract the volume of the other. So to make this problem a little bit more interesting, I cut it like this. Okay, so here, so this is the region. Okay, so now we revolve this. Okay, so let's give some, we need angles there. Okay, so this angle, so say this angle is alpha 1, this angle is alpha 2, the whole thing. So we have alpha 1 less than alpha 2 and less than pi over 2. Okay, so this is what we want. So let me write alpha 2 here. Now, we want to do this since everything is given. Where is my red pen? Here. So a typical ray is like this. So this is our rho. It enters the region when rho is 0. It leaves the region here. Okay, and now this angle is phi. Okay, so we have to find the length of rho when it leaves the region when at the inclination given by the angle phi. Okay, so it's just solving some triangles. So let me redraw the triangles here. Okay, so this is z-axis. So this is our. So first of all, what is this length? Okay, so we are in this big triangle. This angle is alpha 1. So this region is the same as this region. Okay, so what is the length of this side is r. Okay, so maybe first we do that. Okay, so this angle is alpha 1. This side is r. So you see that this side is, this is perpendicular. What is the length of this? R. Okay, so this is alpha 1, r sine alpha 1, right? So that's equal to this side. So this is r sine alpha 1. Okay, so let's come to this part. So we have this thing now. This angle is now phi. This side is r sine alpha 1. This angle is, I want to find this length. I know this side. So this angle is pi over 2 minus phi. So this side is rho. Sine of, well, no, cosine. Okay, so cosine is given. Cosine of pi over 2 minus phi is equal to r sine alpha 1 over rho. Okay, so this is sine phi. So from here, rho is equal to r times sine alpha 1 over sine phi. Okay, so r is constant, sine alpha 1 is constant. We have just sine phi changing as phi changes. And here, you see phi changes between alpha 1 and alpha 2. Okay, so we have time, so I don't have to rush this. Okay, so once these limits are done correctly, so this is the technical part, now we can set up the integral. Okay, so we know where phi changes. Phi changes between alpha 1 and alpha 2. Rho is between 0 and this limit. And theta is free to run from 0 to 2 pi because we are revolving this without any restriction. So volume is equal to theta runs from 0 to 2 pi. Phi runs from alpha 1 to alpha 2. And rho runs from 0 to this number here, r sine alpha 1 over sine phi. Okay. And now I need the Jacobian of the transformation, which is rho square sine phi d rho d phi d theta. Okay. So now we have to evaluate this. Okay, so this one will give me 1 over 3 rho cube. I'll evaluate this here. This will give me, okay, so these are constant, but it will give me 1 over sine cube phi. There is another sine phi here, so actually I'm integrating cosecant square phi, which is easy. Okay, so let me do the next step. So this is equal to 2 pi from theta, because nothing depends on theta. I have 3 coming from this. And then I evaluate rho cube here. I have r cube, which is constant, so I'm taking it out. Sine cube alpha 1 is constant. I'm taking it out of the integral. And what remains is from alpha 1 to alpha 2 d phi sine square phi. Okay, so it looks horrible, but it's very easy. Okay, so if you integrate, if you take the derivative of cosine over sine, in the denominator you'll have sine square, and on the top you'll have plus or minus 1. If you just check the signs, you'll get something. Okay, so this is not one of those mystical integrals. So I'll just, so it turns out that you need minus there. So we have this constant. Okay, so I keep writing this 2 pi r cubed sine cube alpha 1 over 3. And here this is minus cosine phi over sine phi. Okay, so this is the first thing that comes to mind without the minus sign. You take the derivative of this, because when you take the derivative of this, you'll have sine square here. Now, in this case, if you check, the derivative of cosine gives you minus 1, and then you have minus cosine times the derivative, so you'll get minus 1 on top, and this minus corrects it to bring this one. So this is from alpha 1 to alpha 2. And when you simplify this, okay, so when you simplify this, let me write it here. So this is the third time I'm writing this 2 over 3 pi r cube sine cube alpha 1. So this is, well, this one will come with positive things. So this is cotangent alpha 1 minus cotangent alpha 2. Okay, so that depends on, we were expecting this, of course, to depend on alpha 1 and alpha 2. So this is the answer. We can also solve this using methods we learned in the last semester. Okay, so what is the method here? So also another solution, another method. Okay, so here I have this. I have this line, and I have this line from here. Okay. So again, I'll do the same thing. This part is again, so let's say this is x, this is y. Okay, so the problem is the same thing. I'll revolve this around around the y-axis. This point is r sine alpha 1, as we found here. Okay, so this angle is, so these are lines. This angle is alpha 1. So this line is y equals cotangent alpha 1, right? Because this is cotangent alpha 1 x. This line is y equals cotangent cotangent alpha 2 x. Okay, so I take an arbitrary x here. Okay, and I consider this length. I revolve this length around y-axis. Okay. So volume obtained by revolving this red line around y-axis, okay, so is equal to, I integrate, well, I find the length of this. The length of this is cotangent alpha 1 minus cotangent alpha 2. Okay. It travels a distance of 2 pi x. Okay. 2 pi x. So here I have a cylinder like this. Its thickness is dx. Now I have a volume. I add these volumes from x equals 0 to x equals r sine 1. Okay? Adding these things means from integrating to r sine alpha 1.
Shouldn't x be squared? Because it comes from the length, I guess.
Yeah, here, yeah, you are right. I have this x, so here, okay, let me put this x here. No, let's put this x here. Okay. So this is the length, as you are right. This is length, so the length of the red line. And this is the distance it travels. And this is the thickness. If you read integrals like this, then it makes sense. Okay, so here you are describing some small volume defined at the point x. You imagine it like that, and then you add all these volumes for all possible values of x. Our possible volumes of x is from x from 0 to r sine alpha 1. When you integrate this, you are integrating x squared, so you'll get x cubed. Okay, so that will give you this cube here. And when you are integrating x cubed, you'll get 1 over 3. You have this 1 over 3, and you have this 2 pi here. And of course, this is a constant. Cotangent stuff is the constant. Okay, so here you get the same volume. So in this problem, this was easier. Okay.